What's new? Oh.
So Nancy unplugs everything.
Yeah, that'd be classic. You're all set? Okay, let's go ahead and get started. My name is Gary Stephenson. I'm with Lindquist Corporation. Our background at Lindquist is we support United States Air Force in MILSATCOM. We have about $40 billion in ongoing contracts and acquisitions that occur at Space and Missile Center at any given time. They're all unmanned. So you might ask, why am I presenting a paper on human rating requirements? The short answer is I just recently joined the Mars Society. I'm very interested in this topic. And so I thought, how could we apply standard mission assurance practices to the problem of human rating requirements? And so being the Mars conference, a Mars mission was a good place to get started on that. So the outline is going to be, I'm going to take a look at what has NASA done recently for human rating, what procedures have they used, and how could those procedures be applied to a Mars mission. So I'll go through a four-step process. We'll go over the details of each of these steps. The first step is having a process. The second step is having a mission. Third step is then applying standard design guidance to that mission. And then proving, fourth step is putting together a human rating certification package, is the name of it, that proves that you've gone through all those steps. And then I'll go through a few recommended future tasks, because when we go through these, we'll find there are some technology gaps right now. And so a gap analysis when you go through these human rating requirements against what we'll have to do to make a Mars mission work, there's a few things that you've already heard about, like radiation, artificial gravity, and so on, that kind of jump out of this. Okay, so what has been done in the recent past with human rating at NASA? Their most recent human rating exercise was on the Constellation program. This slide is adapted from a slide that was presented by NASA personnel. And you'll see two different aspects entering the interface requirements, the integration, human system integration requirement set that they developed for Constellation. It was, first of all, a NASA procedural requirements that provided the authority or the process guidance for the Constellation mission. The second aspect was this kind of grab bag of domain expertise and not corporate knowledge, tribal knowledge, I guess you could call it, of standard practices and specialty engineering sorts of things that are typically applied to keep humans alive. So there's been 50 years of work that NASA's done on human-rated systems, and this NASA Standard 3000 captures much of that guidance. So you've got the process guidance and you've got the design guidance entering into your human system integration requirements. So in a nutshell, it's defining a habitable environment. What environmental aspects are required to keep people alive on a mission? What sort of parameters are we going to look at to protect the health and safety of the crew? It helps the focus of proper integration to human system interfaces. That's the purpose of these human system integration requirements. So how would we adapt this to a Mars mission then? We saw in the previous slide, it's inherent in this process guidance, but it's not really very explicit that there's a reference mission. And we heard about before, Dr. Bob Zubrin talked about, let's focus on the mission and the mission assurance and make sure that mission success is what is guiding our design. And the mission success includes keeping people alive on the trip out, on the stay there, and on the trip back. And so that mission objective, that set of objectives and reference missions is what's going to guide us. So it's important to have the process, of course, that's step one, to follow in terms of this human rating. Step two, though, should be what is the mission? The mission is to keep people alive on a trip to and from Mars. And then third, we can apply the standard design guidance that NASA's collected over the years in terms of the technical knowledge of what it takes to create an environment to keep people alive. This then is overall, this would apply to any manned mission, but specifically, we're going to see how it applies to a Mars mission. Okay, I want to back up to point out these human system requirements are going to be applicable to all mission elements. And so I show a stack of them here because there are a number of mission elements that are going to be involved in a trip to Mars and a return from Mars. So this is a very general picture of sort of a schematic of the different elements you would see on a mission to Mars. You've got, first of all, Earth rendezvous. You have to have something bringing you from the surface of the Earth on your launch vehicle and probably rendezvousing with a transhab, with a transportational habitat. Then you've got the transhab, or as I'm labeling it here, T-hab itself, that's going to be your living quarters for the journey. And the ERV may or may not come along for the ride. Then you have to have the Mars excursion vehicle on the other side that's going to take you to the surface of Mars, from orbit to the surface of Mars, and return you as the ascent vehicle. And during that time, you may store the T-hab in a storage orbit for your return trip. And we also heard an interesting idea today that you could just dock it to Deimos, because Deimos has such a microgravity anyway, it's essentially a docking orbit. So this, in general, you could put it in any storage orbit, but in particular, you could pick the Deimos orbit and store it there. And then you've got the surface hab, and that's your fourth element. So these are sort of, in general, the kind of pieces of mission equipment elements that you'll see that have to be habitable. There are other mission elements, but these are the ones that people are going to live in. And when you look at flowing down these human rating requirements, they're going to flow differently to these different pieces. You're not going to spend the same amount of time in the ERV or the MEV as you are in the T-hab or the S-hab. You'll probably be spending 8.5 months each way in the trans-hab. On the surface hab, you'll be spending more like 18 months for a typical mission profile. Now, we don't have a standard reference mission yet, but that's typically what you'll see for suggested missions. So when we look at the flow down then, this is the process that I've outlined and extracted having looked at the NASA guidance. And it's really difficult to boil it down because it's 50 years worth of guidance. There's dozens and dozens of human rating requirements that NASA's generated. And so I've tried to apply mission assurance techniques to this set of guidance to sort of untangle the web of guidance that NASA's generated over the years. The guiding document in terms of process is this NASA procedural reference. So you would flow that then, make sure that you're using that same process guidance for this entire process of developing these integration requirement sets for your ERV, T-hab, surface hab, Mars excursion vehicle, and so on. Applying the mission objectives, so this means we have a reference mission or a set of reference missions. And it's important to establish a range of parameters for each important parameter set in your reference mission so that you can design this equipment set for not just one single point design, but for a range of mission designs. And so when you're defining these reference missions, you might define a range of reference missions where the trip could be 8 months long, it could be 9 months long. And if you're doing it that way, you're going to be driving down your cost in the long run because you'll be able to do a lot of reuse with this mission equipment set. Same with the surface hab. You may design a surface hab first to be stocked for 2 weeks, but it may have the design features to support a 1.5-year stay. So that's something to keep in mind when these products are being developed. And then, of course, step 3, there are standard things like safety, how do the controls operate, mission control, there's contingency operations, and so on. We'll go into details on all 3 of these steps, and a 4th step as well, in terms of building the certification package. And we'll see the details of what each of these steps entails. And there's also a companion paper, and I have a link at the end of this, that has much more detail in terms of a survey and a summary of all the NASA guidance that has been generated over the years, stacked into a summary in terms of these 4 steps. So this is the first one. We have to have a process that everyone agrees to, an agreed-to process. So it's built off of NASA standards. However, say, for instance, you're a commercial company, and you don't really have to comply. Say you have commercial customers, you don't really have to comply with NASA standards. You'll still want some kind of process set in place so that you can establish a mission assurance program of your own. And so NASA, having spent 50 years developing this, why not adapt your process to match this particular process, since all of the key elements are there already anyway. So for instance, number 1, document reference missions. If you don't have a reference mission, you're not going to be able to levy a mission assurance program against anything, and you'll have design drift. You won't know what to design. So the absolute first thing you have to do is document a reference mission. There are other things in here. I won't read every single one of them, but you're going to have utilization, have a philosophy of how does the crew operate the craft in every particular phase of the program. Are there safety? Is safety baked into the design? Have the safety analyses been performed to make sure it's a safe design? What is safety? Is 99% probability of return? Is that defined as safety? Or if you're a commercial operator, are you going to have 99.939% reliability in terms of safety? Those are decisions that have to be made when you're defining your reference mission. And so that'll be important to define when it comes time for the safety analysis, because you're going to have to show and demonstrate, at least analytically, that all of the things that can go wrong with the mission set that you have fit within that 1.1% that you've allocated to yourself, or 1%. It depends upon what number you decide is safe. Evaluating workload, human in the loop, human error analysis. If there's a big red button that says don't push that button, and it's sitting there where your elbow is lying, and you bump that button, that's probably not a good, design. So human error analysis says, have a design that if a human makes a mistake and does the wrong thing, it doesn't blow up your whole mission, that there is a way to recover from mistakes. Validating the system capabilities. Flight test is an important, you have to establish a flight test process. You have to establish a certification process. That, in a nutshell, is the process guidance. That's step 1. And the paper has much more details on each of these steps extracted from NASA guidance. And you'll see these reference numbers, these mysterious numbers here. Those are all references that I have listed at the end of not only the presentation, but the paper, same reference numbers. So, and I think they're going to include this presentation on the DVD sets that are handed out. Okay, step 2 is developing the mission requirements. These are not all the mission requirements. These are just the mission requirements applicable to the scope of this paper, which are human spaceflight mission requirements. So in particular, humans have a range of capabilities. We're all built differently. And so that's all specified over the years with human factor guidance that the military and that NASA has defined. There's also the regulation of natural and induced environments. Providing for water and air is fundamental, and you'll see that will drive a lot of your design choices, and you'll have to determine what are your resources that you're bringing with you in terms of food, water, air, enabling crew functions, waste management, exercise, providing for the proper space medicine. You're out there alone on a Mars mission. You're going to have to bring your own medicine with you to the extent that you can. Those are the kinds of mission requirements that touch human spaceflight certification. So, and laid on top of that are the constraints of how long are the trips, and how long is the stay on Mars? How long is the return? Is the return trip the same as the trip forward? Can you bring resources back? Do you have plants waiting for you on the surface to bring back? All of that is going to have to be part of your reference mission to define how much water and air and food you bring with you versus how much you capture on the surface of Mars and are able to return with or use while you're on the surface. This is an eye test. I don't expect you to read this other than to know that there are standard budgets for lunar and for lunar transhab and lunar surface habitation that have been developed over the years that define all of the provisions required for both the trip and for the stay. This particular case happens to be the lunar cases, and if you get the PowerPoint slide, you can look at all these numbers in detail. The important message here is that there are a number of provision requirements. You have to track all that. It has to become part of your mass budget and your volume budget. And if you want to do oxygen recycling or water recycling, there's an efficiency associated with those processes, and there's going to be reliability associated with that reprocessing of water and air to keep people alive, and it is life critical. So these are life critical functions. You either have the resources to provide for them or you have the resources to recycle them. Since these numbers are just for lunar cases, I wanted to at least list some Mars cases. There are tables in Larson's book, Human Space Flight, and because of copyright limitations, I couldn't reprint them here, but they're available in that reference, and that reference is available at most technical libraries, or you can purchase online. The third step then is applying the standard set of specialty engineering and design guidance that NASA has collected over the years on human spaceflight. So it is things like system safety requirements. It is control of the system. What control requirements does the system have that we are going to levy on it? Even if there are autonomous functions, it's still a requirement, for instance, that you have to have a manual override, so that if the autonomous system breaks or malfunctions, you can have a manual override and operate that system manually. There has to be a requirement for closed loop, human-in-the-loop control of the flight equipment. If you have thrusters and so on, you have to be able to operate that. You have to be able to present the data to the crew to be able to interpret how to do that. What's your situational awareness? You have to provide that to the crew. And then you have to have survival and abort requirements. In this case, the survival means, say something goes wrong that pooches the mission. You're completely not going to come home. What are your contingency operations? Are there lifeboats set up along the route that you can use as a fallback position? Or can you return to the surface of Mars and use that as a lifeboat? You have to have a contingency ops plan to cover all of that, laid out and agreed to and defined as part of your system design. Proximity operations, there are a specific set of proximity operations because of the Mir accident and other close calls that have occurred over the years. You need to certify new vehicles before they can be used for proximity operations. So there's a specific set of requirements on that. How are we doing for time?
You're good.
Okay. Okay. So then the final step 4 is building a human rating certification package. Well, what goes into that? During every step of the process, you collect what you need to feed that certification package. There are things like the process compliance has to be in there. The reference mission definition, as we talked about, has to go in there. So as you're building these integration requirements, you can be collecting that. As you're going through your design, your mission design, you can collect the design and analysis compliance. As you're producing this hardware set and software set and testing that, integrating and testing it, you can add inspection compliance. You could add integration, validation, and verification. You want to validate and verify and test as much of this as you can in pieces before you integrate it, and then you want to test as much as you can at a vehicle level before you go to Mars with it. And so some of the suggestions I'll have at the end of the paper is what kind of tests can we apply to this Mars-specific equipment. to using the ISS and possibly using lunar rendezvous to check these systems out before you go on this awfully long journey, because the moon is 3 days away, 6 days away if you take a leisurely pace. Mars is, 6 to 9 months away, and so something goes wrong there. It's much more critical. And then the end of step 4 is maintaining. You get that human rating certification package. Say you've agreed on the certification package is compliant, you've done the checklist, and the people that you've decided are the authorities have signed off on it. You still have to maintain your certification, which means every time you go through a configuration change, you change something, you have to go back and say, well, how did it impact my certification package? And this is a great tool. The certification package is a great tool for auditing configuration changes. So in the checklist then, you've got your reference missions, you've got your contingency operations, you've demonstrated that you've validated and verified all the technical requirements, you've performed all your safety analyses, you've checked off all your human system integration requirements, you've validated and tested all your critical performance type functions like life support, you've performed a flight test of all components, then, and you've documented that you're doing configuration management, and you can't just change something out without keeping track of it. That all goes into the human rating certification packages, and now you're certified. So, where are the trip points for Mars? If we go all the way back to step 3, let's go back to step 3. Down here, maintaining crew health standards. NASA defines 3 extremely useful health standards: fitness for duty, where you're measuring functional capacity. For instance, people who are working 12-hour days can pull that off for so long. The NASA standard is 8.5 hours, because it's already hard enough to live in space, and then you actually ask them to work 12-hour days. They can do that for a short period of time, but they'll sooner or later their functional capacity will be degraded. That's an example of an FFD. Space permissible exposure limits. This is where you're being exposed to something like radiation. There are limits set up for that. They're already well defined, and so they're not, this isn't something we have to have a debate about. You either meet this or you don't. Same with permissible outcome limits. This is where you're actually measuring biological changes, like bone loss. Bone loss would be an example of a permissible outcome limit, where you're allowed to lose 2 sigma of bone mass. So we'll see that as a constraint. So these are the kinds of things that will come into play on a Mars mission that would not have on a lunar mission. So now if we go down here, radiation abatement trades are going to be required because of this radiation limit. Artificial gravity trades are going to have to be looked at because of this bone loss limit. There are also operational control trades. This is an awfully long journey. If you have a small crew, they may or may not be awake at the same time or asleep at the same time. You're going to have to have a level of automation, and you're not under ground control. You're too far away to have ground control in many cases. So there's going to have to be a new standard for operations control, and there's going to have to be a new standard for contingency operations, as I discussed a little bit. The lifeboat situation will be different. What if something goes wrong? Are there going to be other ways to get back to Earth? A radiation impact, just very briefly. When you look at, they call it READ, it's radiation exposed induced death. READ sounds better somehow. It's 3% is the NASA requirement. That means that only 3% of astronauts can die of radiation induced cancer. That's the limit. And if you look at the ages here, older people are going to lose fewer years, and likely something else is going to kill them. And so you'll see the numbers. You're losing more years if you're young off your life than you are as you get older. And also there's kind of cut points in terms of what is 3%. Certainly, 1,000 millisieverts, which is like 100 rem, that's about as much as you want to push the radiation exposure. Thank you. So I don't have a lot of time to go over these graphs in detail. The point of it is you have to look at radiation abatement. They did, thank you, they did instrument the Curiosity as it flew out, and they got to 20% of these levels just on the flight out. So if we look at 20% on the flight out, 40% on your stay on Mars and 20% on the fly back, we're kind of already in the zone where even if you didn't do much, An astronaut can make one trip. He's not going to make 2 trips, but he can make 1 trip. If you want to get it better than that, you could do water shielding. That would cut down on the solar wind type exposure. And as well, you could do a magnetic field, artificial magnetic field. You just run whatever current sources you do through a coil before you use your current for anything else. And that creates a little portable magnetosphere, and it helps deflect a little bit some of the solar flux. For real serious gamma ray abatement as well as ion abatement, you can look at burying on Mars for your SHAB. The other problem area is bone loss, which really argues for artificial gravity of some kind on a very long mission like this. Obviously, on the surface of Mars, you're not going to get the same bone loss. This is just a standard graph, and what it says basically is people who are 2 sigma down from normal are getting into osteoporosis. You get into osteoporosis, you get some rate per 1,000 per year of hip fractures. You do not want an astronaut getting a hip fracture when he gets to Mars. And so the NASA limit is a 2 sigma loss for the whole mission. I think that's a reasonable limit. You just have to live with that limit, which means you're going to want to look at artificial gravity trades. I show the hamster wheel. I don't know if you've seen 2001. There's a little rotating piece inside the ship. There's all kinds of problems with this. You rotate a piece, sooner or later there's friction, it's going to make the whole ship rotate, right? So you have to have a counter-rotating thing, and you have to have energy all the time, and then your counter-rotating thing isn't the same size as your rotating thing, so you have something in the rear to take out that moment. And so it's just a lot easier just to spin the whole spacecraft on a tether, and plus this has never been tested in real life in space. It's been tested on the ground. And by the way, it makes people sick because of tidal effects. In space, you can get the moment long enough where you don't get tidal effects, you don't feel the gravity difference, you can spin the whole thing. This tether experiment ran for 10 years. The tether didn't break. Now, it wasn't a 1G tether.
Until it did break?
It did ultimately break. It lasted for 10 years, but like I say, it wasn't a 1G pull. So we need to get this tested and get better loads on tethers. But that is certainly something that has at least been tested. So I want to wrap up. Ultimately, all these have to be decided as part of your design trade that comes out of this process. So in conclusion then, the process, you could look at it very simplistically as a 4-step process. Get a set of processes that's agreed to. Get a reference mission or a reference mission set that's agreed to. Get a design that meets the requirements, at least on paper, of that reference mission. And as you're implementing that design, document every step of the process into your human rating certification package and get that certification. That's your way forward. Now, how far are we? Well, I've sort of outlined kind of the process. Obviously, you would need, depending upon what your authority is, are you a commercial company? Are you a NASA provider? Are you a military provider? You're still going to need your ultimate customer to agree, that's a good process for me, and I like that process. You're going to have to get your customer to agree on a reference mission set. In some cases, your customer might be the American people. And some reference mission sets will be acceptable and some won't. And then the technical design that fits that reference mission set. Right now, we have some low technology readiness areas that I've outlined, the radiation abatement, the artificial gravity abatement, that trades there. And then operational control and contingency ops I didn't really discuss other than we're going to have to look at how to do that. Some things that might be helpful, test this artificial gravity system in proximity to the ISS. So if something's going wrong with it, you can instrument it, or you can have a crew and they can escape to the ISS if something goes wrong, or you can just do it unmanned and have it monitored from the ISS. And then in terms of some of the other vehicle testing, you could possibly look at doing lunar ops to check it out and do the validation and verification with lunar ops. Once everything's tested, we can't forget, last step is go to Mars. So that's my talk. Thank you very much. Question in the front.
Well, first, that was an excellent presentation. I have before my life in manned space. I think it's very important because most people think you put a rocket on the launch pad and you launch it and that's it. Now, I have two small questions. The first one is SpaceX. you know, they intend to go from this unmanned mission where I think NASA has a minimum control in the approach, but before they didn't really care. Would you agree, or would you think that this Ben rating would be significant and very expensive for something like SpaceX capsule?
Yes, yeah, the question is, SpaceX, where are they with man rating? Is it going to be a significant cost? And of course, the answer is yes, quite significant, but they're being paid for it, and they just received another $440 million to take what's right now rated for proximity ops to ISS and bring it up to manned rating. And so they are being paid. They just received a contract, as did Boeing, and to half measure, Sierra Nevada just received a contract to try to pursue that man rating.
Do you have an idea if the rocket has been man rated already?
No, the rocket has not been man rated so far. I can't speak. Is there anyone from SpaceX that could speak to it? Okay. I have no.
I have a second question. If you have a manned Mars mission because you have limited launch capacity and you need to assemble in space, I think, wouldn't this significantly decrease the probability of success because you have very long time spans of hardware being in space, waiting for the next element being mated and so on?
You would have to look at the trade of how practical is it to launch really big pieces, and how proven is your launch vehicle versus a very reliable launch vehicle that launches small pieces. And then there's some issues associated with mating them. Of course, that's also a risk source. So I would say a risk trade is appropriate there. I don't know what the answer would be.
Thank you.
This has to be the last one.
Oh, okay.
Okay. Two things seem to be left out. It doesn't have any inkling in there about how to measure and human rate the entry descent landing system. I didn't see anything in there about human rating for in situ propellant production and Earth return. I mean, those two are some pretty interesting bits of technology that also have to be folded through this grinder.
Sure. Yeah, and presumably, if this ERV is being used for descent and return, and this is being used for ascent, dual purpose, then those requirements would have to live here.
Well, wouldn't the use of sample return and using in situ propellants be a great boon to getting the statistics required for human rate on that way back?
It would be, and those would have to live here on the ascent vehicle.
Would be a way
Yeah,
to get
that would be a part of it. Yep. That's how you'll factor in. Okay, all right. Thank you very much.